So we are back again to considering the eigenvalue problem. Right now, we know what an eigenvector is. An eigenvector is a particular vector which an arbitrary tensor transforms without rotation. It just elongates or contracts. And when that happens, we say that that particular vector is the eigenvector of that tensor. And the amount of contraction or elongation or the scalar multiple that you get is the scalar value called the eigenvalue. So you have the eigenvalue and eigenvector defined by that geometrical relationship. You know that a tensor transforms vectors, but this particular tensor transforms the vector in such a way there's no rotation, no change in direction, only changes in magnitude with a particular magnitude factor or scalar factor, which we call the eigenvalue. And the eigenvalue, eigen there is a German word meaning characteristic. So when you read other textbooks that talk of characteristic values or characteristic vectors, they are talking exactly the same thing. If you are in material science, mechanical engineering, civil engineering, or any engineering that looks at stresses and stuff, eigenvalues are the principal stresses and the eigenvectors are the principal planes. And there are interpretations in virtually every area of engineering. So it's a very important practical issue. And the meaning. So once we have the meaning, we can now go and work out the math. Like I told you, the math is just, once the meaning is always behind your mind, the math is not that hard. So we begin from the simple equation. That is the operation of T on U only gives us the scalar multiple of U, nothing else. I want to see whether the classes are awake. What we have on the left-hand side, is it a vector, a scalar, or a tensor? On the left-hand side, what does the left-hand side evaluate to? Vector, scalar, or the left-hand side of this equation, what does it evaluate to? Vector or scalar or tensor? Okay, some people said vector, okay. What about the right-hand side? What does the right-hand side evaluate to? Right-hand side. What does the RHS? What does the RHS? Okay, so it's a scale vector, Boulevard is still a vector. So it's a vector equation. Now, suppose I transfer the lambda u on this side to the left-hand side. We'll have a 0 on the right-hand side. That 0, what would that 0 become? Is it a scalar 0 or a vector 0 or a tensor 0? What type of 0? The way, okay. So it will be a vector 0. So you can see that this is a vector equation, and whatever we are doing, whenever every term is fully evaluated, what we have is a vector, despite the fact that T is a tensor, and U is a vector, and lambda is a scalar. So that's good. So we're going to do just, you don't get the question. Okay, let me, say, okay, he doesn't understand the question. If we transfer a value from the RHS to the LHS, what is left on the LHS? Now, who didn't get the question? I think it's Oluwa. Somebody said he didn't understand the question. Is the question clear now? Yes, Israel Olaoye, can you respond if you understand the question now? Okay, so it's clear to you now, Israel. Good. Please, just be like Israel. If anything I've said is not clear, please stop me and ask the question. I will pay attention to you as long as you are serious. The only thing I don't want to hear is people who think we're joking here and try to crack silly jokes. I'm not here for that. So let us go on. So let us now move into just doing that. So here, I've just done that. Here, I've transferred lambda u to this side. If I transfer lambda u to this side, you can see that what I have on the right-hand side is a 0 vector. So, and I say it is equal to T minus lambda I u. Now, why can't I just say it's equal to T minus lambda bracket U? That's the question again. Why not T minus lambda in the parentheses? Why don't we just have T minus lambda in the parentheses? Why don't I just have T minus lambda in the parentheses? Yes, we are going to get a dimensional problem that you cannot just subtract a scalar from a tensor. So this is to show you that that is the case even when you break it into components. Let us move step by step. You can see that T is, we can write T in terms of its components as Tij, Ei circle times Ej. This is T in its terms of its component, and this is U, Uk, Ek in terms of its components. Similarly, lambda, Ui, Ei in terms of its components. So this equation is the component way of writing everything. And if we open this dyad bracket, operate it on Ek, so you can see that you have Tij Uk and you have Ej dot Ek, which means that you have Ej dot Ek here, and the chronicle delta here changes this K to J. So that's why you have Tij Ei Uj minus lambda Ui Ei. So you have Ei on both sides. You have Ei on both sides. So if you want to remove Ei, you can have here Tij Uj lambda Ui. And the only way you can turn this Ui to Uj is to have a delta Ij here, which again gives you the identity tensor here. So no matter whether you work from the component side or you work from the direct side, there has to be an identity tensor here for this bracket to be valid. So this is the correct equation now. This equation now that Tij minus lambda delta Ij Uj Ei is the zero vector, or that T tensor T minus lambda Iu is equal to 0. So you have this, a tensor obtained by subtracting lambda I from T, operating on U gives us 0. So we now want to solve that problem. You have a tensor operating on a vector giving you the 0 tensor. We now have to go back to the fundamental law of linear algebra in order to get something out of this. From high school, you knew that if the product of two scalar variables vanishes, at least one of them is 0. If you are sure that one is not 0, then you are certain that the other must be 0. So if you have two things, their product is 0, and you know that one of them is not 0, then the only conclusion you can make is that the other one must necessarily be 0. No one can blame an engineer if he does not know that a similar rule exists for larger objects like vectors. For example, if vector u is not equal to 0, there is a rule that says the only way for the equation mu to be the 0 vector to be possible is that the determinant of m must be 0. The determinant of m must be 0. If not, because in this particular case, I claim that u is not equal to 0. And we justify that claim. I am claiming here that we cannot say u is equal to 0. Am I justified in saying that? That is the real kernel. If I claim that u is not if I claim that u is not 0, that is, it's not a 0 vector, If I say U is not a zero vector, am I justified? If I am justified, why? If I'm not justified, why? If you don't understand, I will explain. But let's see whether anybody can say whether it is justified and explain why. I'm claiming here that U cannot be zero. Okay, two people said it's justified. It can only be justified only and only if two tensors in the bracket are equal to each other. Okay, you have tried, but let me tell you why we can say U is not equal to zero. Look at this equation. We are saying that the question we ask is this: suppose we have that for a tensor we do not know to be any of this situation, we have a situation where TU is equal to lambda U. So what I'm saying is that I am not dealing with a trivial vector. I'm not saying zero. Because if that in my presupposition, I'm assuming that it can be any vector. If it can be any vector, we will exclude any particular, it can be anyone. So we cannot say it's therefore zero. It can be anything. It can be zero. It can be, if it's zero, that's a trivial case, but it can be other things. So we cannot always, you cannot just be said to be zero because it is capable of taking any value. And this equation will still be true. So because by our hypothesis, we didn't say that U is zero. Therefore, I can say U is not zero because it doesn't have to be zero. So if it doesn't have to be zero, then it means that the determinant of this tensor, not the tensor T, determinant of the tensor T minus lambda I, the tensor we form with T minus lambda I, their determinant must be equal to zero. That is similar to the rule that if two scalars are multiplying each other, that one and they are zero, one of them must be zero. If you know one is not zero, then the other one has to be zero. So, therefore, in our equation, the last slide, we have that T minus lambda I U is equal to zero. Therefore, the determinant of T minus lambda I must be equal to zero. This zero here, is it a scalar or the zero in this last expression? Is it a scalar or a vector or a tensor? Oluwatife, you are wrong. The last zero here is not a vector. This zero in this equation. I hope you can see where my Oluwatife, you are wrong. It's a scalar because the determinant of a tensor is a scalar. When we say determinant is zero, it has to be a zero scalar. So whenever because remember that when you counter zeros in our expression here, in our expressions here, it can be scalar, it can be vector, it can be tensor. So to know at every point in time which one you are dealing with. Is it a scalar or a vector or a tensor? Which one are you dealing with? So you must know which one you are dealing with at any point in time. Okay, so we now go to the definition of a determinant of a tensor. So by the definition of determinant, let us say it is M, it will be MA, MB, MC in its scalar triple product divided by ABC, where A, B, and C are any set of linearly independent vectors. That's all. That's the determinant. That's what it is. It just the tensor we are dealing with here is not just T, but T minus lambda I. And if T minus lambda I is equal to 0 over ABC, even that means that the numerator itself must be 0, because once we know that the denominator is not 0, for this quotient to be 0, it must mean that the numerator is 0. So we can say that this numerator is 0 and it's a 0 scalar. And that, therefore, means this equation we have in the red. And is that, can you see from here why this is true? I want to know if there's anybody who cannot see it, if there's anybody who can see it, and let me have your responses. So your responses determines what I do next. Is the last expression obviously resulting from an ultimate Is it obvious? I give you a minute to think about it. Can you see this from this one? Oh, I'm writing to Israel now. No. I want to write for everybody. So everybody, please, I will respond once I get. Okay, Matthew said he can't see it. Who else didn't see it? James, please say whether you can see it or whether you cannot see it, because it is going to determine the vigor with which I explain it. Because what is important next is that you can understand that this last expression is obvious and that follows from the previous one. Please look at it. I will wait for a full minute. I'll wait for a full minute from now to be sure that I have enough responses and see whether there's anybody in the class that can see that the penultimate equation implies the last equation, the last expression. Please don't be quiet. Respond. So we have 30 seconds to go. There are some people who are in class who are not responding. Can you see it? Can you not see it? Because it's a critical step. That's the most important step. Is it obvious to you? If it is not obvious to enough people, I will explain it in details. And after I finish explaining, I will ask again whether it's now obvious. Okay, no, I've seen enough answers. So it's not obvious. So what I'm going to do in the next 2 slides, I want to make this expression make sense as something that results from the previous expression. First of all, the question I'm typing so that now I'll give you a minute to answer that question. Do you remember that when you have 3 vectors separated by commas in a square bracket, that we are referring to the scalar triple product of those 3 vectors, and that's what we have here. So you can see that what we have here is a scalar triple product. So that is all you need to know in order for me to establish the next statement. Okay. So let me go to the next slide now. So good. So I know that this statement is not obvious to the class, and I'm telling you that in the next 5 minutes, it will be obvious to everybody. So pay attention while I make it so. The tedium in the above sum is easily overcome upon noting that we are dealing with a triple product of vector differences. For example, if I have A1 minus B1, A2 minus B2, A3 minus B3, even if we are not talking about triple product, if I multiply these 3 together, how would we do it? What we have is that you take 1, 1, 1 from each bracket. So you have A1, A2, A3. Then you take 2, 2, 2 from each bracket, which would be minus B1, B2, B3. Then you have 1, 1, 2, A1, A2, A1, A2, B3. And that would be a minus because then you have 1, 2, 1, A1, B2, A3. A1, B2, A3 would be a minus. And then you have 1, 2, 2, A1, B2, B3, which will be a plus. Then you have now 2, 1, 1, that is minus B1, A2, A3. So B1, A2, A3. So you must have this all this, and that is the result. Let us say you have the triple product of the difference of 2 vectors. I don't know whether we can drink this down. And that is, if that's clear, then I can move on. I'm not moving on until this stage is clear. So if what I've done here is clear to you for A1 minus B1, A2 minus B2, A3 minus B3, if you can see that the last expression is what I will get there. So I'll give you 1 minute to drink that down. Tell me that is clear. Well, Nkega. Okay. Nkega, what you do, multiply them, just ordinary multiplication. Just multiply them, okay, just multiply them, not triple product. How will you do it? Just three product of 3 brackets, and each one is just a subtraction. Try that and tell me what you get. You just have A1, A2, A3, A1, A2, B3, that's what you get. So try it out. Just product. The way you do it, just do 2 first, then do the third one. Work it out. Don't try and just look at it. I'm waiting. Well, since so many people are slow to understanding this, I want to create another slide and work it out for you. Let me work it out for you. Where are we? Okay, so can the class see what I was talking about? just take it as ordinary multiplication and it will still work. Those are the 8 things. That is it. That's how you do a triple product. It doesn't matter whether it's a triple product or any product, whether it's a triple vector product or any triple product, that is what you will get. You will have to have these combinations, 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2. There are 8 of them. Work it out. The product of that is it. So can I let me just type my question now because it is easier. Can I assume that it is clear? Is there anybody who is still having difficulty with what we are doing here? Is there anybody who is still having difficulty with this right now? Because remember, my business is to make sure you can see that this follows. Do it in 2 steps. The first thing is, do you agree that if we have the triple product A1 minus B1, A2 minus B2, A3 minus B3, if we write everything out, this is what we get. If you accept that, then we can go on. Is it clear now? Is this far? Is it clear at this point? I'm not getting answers. Is it clear? Please just go to the chat room and tell me if it is clear, because I want to move on. So it is clear now. So let us move on. It's clear. Good. So now what we are going to do next, is that instead of we will take A1 as TA, A2 as TB, A3 as TC, B1 as lambda A, B2 as lambda B, and B3 as lambda C. We can do that because TA is a vector, so we call it A1. TB is another vector, we call it A2. TC is another vector, we call it A3. B1 is a vector, we call it B1, and so on. If you just substitute those for all these ones in this expression, you will be here. That's all. You will just get it. You will just see it. So that to get to this point is just the substitution. The substitution here will take you to that point. And I want to keep saying that equation because you need to remember it. I'm going to put it again in the So when you make A1TA, A2TB, A3TC, B1 lambda A, and so on, once you just substitute, you will get this expression for the expression before it. That is it. And if you now remember that if you divide everything here by A, B, C, which is a scalar, that is the triple product of A, B, and C is a scalar you can use to divide everything. TA, TB, TC. If you do that, you just have minus lambda squared, and then you have here plus lambda squared of the plus lambda squared in I1, that is the first invariant, and then here you have minus lambda, the second invariant, and then the last one will just be what do you have in the last one? You just have the last one to be the determinant, because TATBTC over ABC is determinant. So what you have in the next line is simply multiplying the thing by a negative sign. That's all. So what you have here is a lambda cube minus lambda squared trace of T minus lambda trace of the cofactor minus determinant of T is equal to 0. That is what this expression now becomes. So, and that is the characteristic equation. This is the most powerful way to really get to the characteristic equation. You get it to step textbooks. They work pages upon pages upon pages to reach this point. If you don't have to work like that, if you stay with the direct form, it is easy to get here, that you don't lose a lot of sweat to reach this point. So you don't, and some textbooks go to components. If you go to components, you are going to write at least 2 or 3 full pages. And that can be very, very laborious. So this is the best way to reach this point. I'm deliberately slow for you to just see that. So what we have that we can either like this, lambda cube minus I1T lambda squared minus the second invariant lambda minus the third invariant is equal to 0, or lambda cube minus lambda squared trace of T, which is a scalar, plus lambda trace of the cofactor, which is another scalar, then minus the determinant of T, which is still a scalar. So is equal to 0. This expression, either in this form or in this form, is called the eigen equation or the characteristic equation, whichever way you like to call it. It is, most textbooks refer to it as the characteristic equation, but if we are to be consistent with the word eigen, it's also the eigen equation of that tensor. It's the eigen equation, and it is a cubic. I want to ask you a question. How many roots will you get from a cubic? If you ordinarily, how many roots do you get from a cubic? Okay, so you expect 3 roots. Those 3 roots are the eigenvector, they are the eigenvalues. You know, that's lambda. Remember that lambda in the original expression is the eigenvalue. So we have 3 values for lambda, and if you put one of them here, you will find the U that satisfies that. You will get the, you will put the 3 of them in this equation one after the other. When you put one, you get one eigenvector. You put the second one, you get another eigenvector. You put the third one, you get another eigenvector. So, and the eigenvectors, you can get them, is what really matters about them is the direction. So you only need to worry about, you can make one of the components arbitrarily 1 and get the other 2 that satisfies this equation. As long as the direction is correct. So that is it. So, but you can get it by using Mathematica. If you just create the matrix form and you just ask for the eigenvectors, it will just give you the eigenvectors. If you ask for the eigenvalues, it will just give you eigenvalues. So you don't have to work that out yourself. But this is how the algorithm they use is based on this equation, and they can work it out using computer. So, okay, so the characteristic equation. The cubic lambda cubed minus I1t lambda squared plus I2t lambda minus I3t is equal to 0 can be solved for 3 values of the scalar lambda. These are the eigenvalues of the tensor. Substituting back into the equation is the way to manually compute the eigenvectors corresponding to each eigenvalue. Of course, we shall not do that. We use Mathematica to compute both eigenvalues and eigenvectors in practical situations. I think I am actually not particularly interested in going beyond that today. I think this is, if you go and drink that down, because what I have discussed with you today is very important, is a kernel of your understanding of engineering mathematics. Eigenvalues and eigenvectors are just so enormously important. And I hope I've explained to you where they come from, what they mean, and how to evaluate them, and why the characteristic equation is correct, and why the characteristic equation, once you know your 3 principal invariants, those are the coefficients of the characteristic equation, the determinant, the trace of the trace of the tensor, the trace of its cofactor, and the determinant. Those are the 3 things that are in the characteristic equation. So once you know that, you know the characteristic equation, you can get the eigenvalues, you can get the eigenvectors, and then you will know everything that is important about the tensor. And I want to stop here, really. I don't want to go beyond this point. You see, it is for you to go and think about this again, see that this implies this. And if you cannot see it in 1 step, you should be able to see it in 2 steps. So work it out. Make sure it is clear to you. Make sure what we did that followed it, how we arrived at this characteristic equation is clear to you. If it is so, then today you understand what eigenvector. You know that when a tensor operates on its eigenvector, it does not rotate that. A vector cannot rotate its eigenvector. It cannot. It can elongate it. It can contract it depending on the value of the corresponding eigenvalue. It will rotate other vectors except its own eigenvectors. It will not. The eigenvectors are immune to their own tensors. It cannot be rotated. Other tensors will rotate vectors except its own eigenvector. I think I don't want to go beyond this point today. I will continue the other issues. So what I want you to do, class, you will have these slides given to you. So please read to the end so that when you are coming to class next week, you can ask me better questions. You can walk through it so that I'm going to start from the Cayley-Hamilton theorem and then finish the issues of spectral decomposition. And that way we will, and then when we put once we get to spectral decomposition, we have essentially gotten to the end of tensor analysis. So I will see, I will check what else is left, and then we can quickly see how to go on. But for now, thanks for your attention. I think we can call it a day here.